Hi there. So we are back to our courses. So I'm just making a small test before starting back because we had this morning an issue with the sound. I just check the sound and we can start it back. This morning an issue with. Okay, let's have a look. Hold. Okay. Summary. So we presented the free member ring. Summary. It look like fine now. So we presented the free member ring. Thiophene. Okay. It look like fine. Okay. We talk about the free member ring, the epoxide. So first thing about epoxide, what you have to know that you have to know that you can open it. The opening could occur under acidic or basic conditions. So one thing very important that you should know is depending on the number of substituent. If you use an acid like H plus, H3 plus, or any type of acid, like even BF3, the first step, you remember the acido basic reaction are the fastest reactions in organic chemistry. So if you use an acid, what would happen? Lewis acid. The oxygen will first coordinate to this orbital, to this empty orbital, forming this intermediate plus. Okay, so the opening could occur at this position or like this. Okay, so you have to keep in mind that it should form, it's under kinetic control. That means you form the intermediate, the most stable intermediate. Okay, so the most stable one is the one that you have more substituent with the most substituents. Okay, okay, so this one is the most stable intermediate because the air give more electron. You have two carbon giving electron. Okay, but and in that form you have only one giving electron. Okay, so this carbocation is more stable than this one. Okay, and with BF3 you form one aldehyde typically. Sorry, here minus plus elimination. and you get this product after quenching. Is NaHCO3. Okay, so you form an aldehyde. However, when you use a nucleophile, typically NH2 minus, an amide, OH minus, here is different. You can attack at carbon 1 or carbon 2. But if you see well, carbon 1, it has 2 hydrogen. Carbon 2 have 1 hydrogen and 1 substituent. And depending on the Donitz angle, which is roughly 40 degrees, okay, 40 degrees like this. So the nucleophile attack at an angle of 40 degrees. What will happen from here or here? You see that here the clash is occur with 2 hydrogen. Here you have a clash with a hydrogen and air or carbon. So you have more steric hindrance at this position than this position. That's why when you have a nucleophile like this, it attack. Okay, it's SN2. If you see the former courses. So I explain what is SN2. That means you have inversion of configuration. But here it's not a big deal. So like this. Okay. So if you have, for example, 2 air and 1 air, okay, it's the same. You have 1 clash with 1 carbon. I mean 1 series of carbon. And here you have 2 clash, so it's hindered, so it cannot attack from here. So under basic condition, I mean a nucleophilic, it attack the least. It attack from here, okay? The least substituted carbon plus inversion of chirality. So in that case, one, two. In that case, you get this product. Okay. So epoxide in other words, Lewis acid under basic condition. In that case, you get an aldehyde, or if you had a nucleophile, you can get if you had a nucleophile, you can get okay. Here you have the mixture, okay, the mixture, because it's an SN1, okay. Here is an SN2. Okay, so an acid, if you have an acid, you form the most stable carbocation. With a nucleophile, you don't you attack directly to do a direct SN2 with inversion of chirality. Okay, so let's come back to aziridine. Give me just 1 second, please. I just take my note then. So this is what we have been doing, working on the free membrane, working on the palladium chemistry also. Palladium chemistry. I just remind you, this is all the heterocyclic chemistry. Okay? Heterocyclic chemistry. Later, I will present the newest later. Okay? I've been talking about aziridine. We have been talking about aziridine. Free membrane. Okay, this is aziridine, and I explained you how to prepare it in the previous courses. So now so we know how to get them. Now we want to know how to remove this amination. Is how to remove this NH. Okay, so for that, with a base, okay. So to remove the NH, I get back the double bond, to get the double bond, okay, to get this product. We use this reagent, forming this unstable, and you get an intramolecular cyclization. So one is not stable, okay, upon heating, you get this product. Okay, so to get back you remember how to do this reaction? Exercise 1. How to get back? There is one reagent that you should use. Yeah, it's common. Same reactivity. Which one? Yeah, I hear it. Yeah, you are right. Triphenylphosphine. Any type of phosphine, I should say, any type of phosphine. Most of them. Okay, and you form. The driving force is a formation of this, because phosphine is oxophil. So that's very interesting to activate for DNA activation. So to get back the amine, okay, now you know it. You use this reagent and you get back your double bond. B equal base, okay. I just remind you two things before we start with we continue with the rest. One thing, I'm giving some advanced course on supramolecular chemistry. With nice PPT, okay? With nice PPT on Udemy. Research Edutica. Second thing, we can form you, we can teach you, and give you some projects specifically for specific project, your projects or common projects. Okay, we teach you, then we help you to develop this project one official university. No need degree. You do the project, you get degree. Even if you have a baccalaureate, you can get PhD. Okay, you can even get PhD if it's a great project. Okay, so we want to it's Research Edutica is a project driven organization. Okay, so if you want to get a degree, and even if you are 16 years old, you can join us. We teach you how to do everything. Then but we focus only on innovation. Okay, it must be an innovative project, otherwise this is only the requirement. We can teach you, we form you, and we can assign you one university where you can get officially a degree. After teaching you, we collaborate with another professor, and we make it, or we make it online with us. All right, free, sounds great. Biochemistry of epoxide, thiophene, aziridine. Epoxide. You can see that sometimes while looking at old chemistry, I like very much old chemistry because it gives you more ideas, more insights. Epoxide, epoxidation is very important to form some elimination. When you have a very hydrophobic double bond containing or triple bond containing compounds, our body, if you take one compound, the process for its drug elimination follow this process to have something to make it more soluble in water. Okay, increase the solubility, increase elimination. Okay, so which enzyme can do this reaction? Even I think it was in 2019. Yeah, Nobel laureate in 2019. She developed a directed evolution of P450. Professor Arnold, Frances Arnold. She got Nobel laureate by tuning not only for the epoxidation, but by using the cytochrome P450. Okay, so double bond get, but she tuned it to many other reactions. Okay, by evolution. wild type. For example, amination. You can think about other reactions which are not unnatural, many other reactions. Wild type reaction. Okay, so let's draw cytochrome P450. To create your how. So it's a porphyrin containing compound. Take. Double bond here, sorry. Here we go. It has water, CH2, double bond here. So one thing, you can see that this porphyrin, the heme, you have an iron. And a cysteine, apical, and this one. Okay, this cysteine is very important. If there is no cysteine, it gives some electron density for the iron. Here it's an iron free at the native state. Okay, all right. So we're representing it as follow. Has a square like this, porphyrin, iron free, Okay, so you have, it's the same representation. What you have to know here, this water is labile. You mean you can remove it, removable. Okay, for example, you had the substrate such as the double bond. Okay, no matter, it will remove, kick out the water. Puff, which activate the, which initiate the activation of the enzyme, the P50 350. So it's an iron free. Then a source of electron. Okay, you give a source of electron to reduce, because the active species iron 2. Then you get iron 2. Okay, now here we go. Then here you need the source of oxygen, dioxygen. Dioxygen is radicalar, interact with iron 2 and to form iron 3. Be careful, because the iron provide 1 electron. Okay, it's an oxidation. You oxidize the iron to form this species. Free. Okay, all right, now we are good. You form this species. Then you need 1 mole NADPH 2, so you have an iron 3 to reduce your dioxygen here to get a negative charge at this position. Oops. So you get this compound. Iron 3O, and you have the substrate nearby. Okay, at apical. Okay, upon acidification, negative charge. Okay, you generate, so you acidification, so you generate a radical, because you need something, you need an heteroatom. You need an heteroatom, or maybe if you want to replace, it's a good question. By what you can replace, you can. My question is if you replace this position by tempo, you can tune the activity of this enzyme with the S, okay, like with tempo or with other type of radical. Okay, so you need this iron. So if you had OH, it gives 1 electron, the sulfide gives 1 electron, to the iron, okay, to get this iron 4. So it's still iron free, okay, it's still iron free. If 2 proton, you form water, okay, you protonate, then you reprotonate it, then the iron push the water, and the sulfide give 1 electron to the iron in one shot. So you get this activated iron 4. Okay, and you remember you have the substrate. So here what it does, it gives this electron, so water is kicked out, so it gives this oxygen to the double bond, okay, and the product is the epoxide. And you regenerate, you regenerate your iron free. And water come back, okay, the water is water, this water, molecule of water, come here and occupy. Okay, then you get your this is the mechanism of the epoxidation. And if you analyze well, Frances Arnold, she just if you want a project like this, you tune this position, you tune it with something that is an heteroatom. You need an heteroatom, or like this, okay, maybe selenide is better, who knows, after it depends of the how it interact, how destabilize the interaction with the iron, okay, the level of energy, hard to say, but it gives some idea, okay. Otherwise, if you don't have it's if it's not well stabilized and not well covered, the enzyme is cannot work after 1 or 2 cycles, because it should be an enzyme on the catalytic amount. So type of reaction catalyzed by P 450. Let's say cytochrome P450. you can form aziridine, or I guess you can form, if you imagine you form this product, cycloaddition promoted, or any new, maybe nitrine would be a good project. You form a nitrine, and I think maybe France. You can go have a look to Frances Arnold work if you want to tune, okay, tune. So you get this product. Okay, then you can open the epoxide with the name in, for example. All right. What is interesting, it's how, okay, sorry, you can have two type of mechanism with iron 4. When you have the substrate, the activated form, you can generate sorry, give me 1 second, just a couple of water. What I like, if you have any question or any ideas, you can think how you can tune this intermediate. This is a very nice intermediate that advise you to change the S. Obviously you can change the pocket, but you can tune the S to not only get a triple bond X. It depends on the X prime. That would be a great project. It's a great project. For example, I'll give you one example. Just an example, okay? If you can make a cytochrome P450 that epoxidize each double bond, you control the epoxidation of all these. You know what I mean? Just an example, then you can get a cascade of. So you can make brevetoxin, mitotoxin in a few steps, few controlled steps. That would be great. I hope I will do during my lifetime the photosynthesis of mitotoxin using this methodology. Mm. Yeah, let's think about it. Okay, we come back to our so we say in French, let's come back to revenons à nos moutons. You know, it gives me a lot of idea this course and this enzyme. You can mix two metals. I checked not many, 3 metals. I checked not many did it. You can make a quantum enzyme. Yeah, with erbium, tellure, iron, like a cluster. Yeah, that's well, it's not the aim now. Let's continue the presentation. If you have any suggestion of courses, of anything that you want me to present you, you can let me know. Okay. If you have any suggestion, I'm checking just. Okay. The aim of this channel is not only to give courses, it's also to give some insight, some scientific research that we didn't expect. We explore all the knowledge and we try to find some new projects and stay humble. Okay. So when you have the oxygen, so you can form a radical reaction. Okay, it's a radical reaction. Oops. Okay, so you can weigh A. You get your singlet. No, I don't want to say. Iron 3. So then it can give electron. Here you break it and you take it back. And you get your epoxide like this. Regenerate your iron. Yeah, okay. Iron 3. This is one of the most probable Okay, next. I will be streaming for 15 minutes and then I'll be back later. Then I hope you are learning a lot. Always write everything with the detail. Spread each idea on the side. Then create some new connectivity to create some new projects. Then another example of epoxidation. Epoxidation. Formation of epoxide. Yeah, I think this format of teaching our own students on a specific topic is the best, and I see it in the project that I'm conducting now. I have 3 complex projects. I think this is much better than getting randomly students that, yeah, that's a very nice format. If any customer wants a specific profile, we can teach to that students what he needs to know and prepare him for the project, and that's the right way to succeed. Innovative projects like this one I show you with Professor Arnold. So coenzyme is very give me another idea. You can involve this coenzyme is to make some macrolide. Like when you see OH blah 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 motif like this, maybe 70% of natural product have it, this type of motif, because it's like addition elimination in series, and this is a building block used by nature. So in that case, for the cholesterol synthesis to make the condensation of two coenzyme, acetyl coenzyme coenzyme A give this product. Okay, and PP, it's PPI, sorry, I, it's pyrophosphate. What is interesting, pyrophosphate, triphosphate, nature uses them a lot. Coenzyme use them through nature use them as activating group. That will be great. That's very interesting. Very, very nice. I like this kind of courses where we explore some new ideas. I have not seen that poorly on YouTube or internet. I think even it's not. I have poorly seen it. Like we explore some courses and we give some new ideas for each chapter. That's cool. Okay. So we come back. There's a very important. The substituent can interact with each other. An elimination like this. Okay. After multiple addition, so you can have multiple condensation. After multiple condensation, it's an activating group, living group. So if you don't know what is pyrophosphate, this is pyrophosphate. Okay. PPI. So here. Nature use it to for the DNA synthesis, this activation. And TPI, but TPI is more unstable. So after multiple condensation, you can get squalene. Oh, here we go. Squalene. Sorry. Double bond. Here we go. Double bond. Methyl. Methyl. Okay. Using cytochrome P450, this is the least, the most accessible because double bond. So you get okay. So you have an epoxide here, okay, the cytochrome P450 generated by the cyto. So what you can see, you can this arrow, it means attack from down. This arrow from up. From the upper side. Down. It alternating up, down, okay? That means when you attack from the up, the CH3 goes to the down, okay? If it attack from the down, the CH3 go to the upper side, okay? I like very much the old paper. It's a really beautiful work, and nowadays it's just really, I don't know. It's several months of work. You see the work now. It's Coca-Cola research. Okay. And if you need to activate the epoxide with H+. For H. So I don't show the stereochemistry for some reason. CH3, CH3, path. Okay, you want the stereochemistry. H. So H here. If this one go up, this one go up. So you understand why now. I explain you why. How to don't forget the aim of research is to make something new. In lifetime, if you make one really new thing, you are very useful. But if you make 2,000 things that are the same, no one knows. You stay the same than people. Okay. There is a nice domino reaction at this position where you have up, down motion, up, down, up, okay, a cascade of rearrangement. That's not obvious to anticipate, but the key is to make the driving force to make the most stable carbocation. H+, okay. So the product is methyl, sorry. Let's draw like an artist. My hand are broken. I'm sorry for that. I broke my hand one day many years ago, so that's why I have troubles to draw. Forgive me for that. I broke my hand. No matter. All right. Then if you isomerize this double bond from here, through here, remove this methyl by the same oxidation. Okay, then it makes some elimination and reduction. Okay, reduce. That's why the idea of CH activation, came from Derek Barton. He used, I know, radical, source of radical to activate this position and make some modification. Derek Barton. So it's always interesting to use some different radical. Okay, A, B, C, X, heteroatom to activate. That's another great project. Very nice. Instead of cycle to play between the cycloaddition and the CH activation. Okay, so after you get cholesterol. Okay, cholesterol. Push well your projects. Okay, it's better to do one in your lifetime of at least 5 of this type of projects than climbing 1000 time hills. 5 Everest, better, so that will make well develop well your project idea, not make number of I don't know what. Sorry, here it's 5 numbering. Okay, this one. All right. This is cholesterol. So just to finish and prove you that I have many other examples to show you that are very, very interesting. So let's talk about the fatty acid. Oxidation of fatty acid. Okay. Arachidonic acid. acid, very important fatty acid. This one, so 2H. Fuse cytochrome. Remember the or to form this one. This one can attack you addition at this position. So you get this product. Double bond here. So I draw it better if I draw it well. Like that. Then after oxidation you can get LTA for the co-train. Okay, so local train like that. Okay, so if you have a protein containing a cysteine, it can attack at this position if you have OH up. Okay, so it attack to form LTC 4. Sorry, here. S protein. Protein, okay, this is protein. CO2H. Okay, so you have many other examples. This is for the epoxide, and we had some problem at this position. I can finish with prostaglandin. This morning we had some problem with the sound, so I finish how you get if you had dioxygen, you need like activated oxygen. So I'll explain you next time how to get an activated oxygen. Form tac, 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 to get, and this one come here. One is like one arrow like this for electron. One like this, that means you modify 2 electrons. You involve 2 electrons. So you get this nice product. Prostaglandine. Prostaglandine. Very important biomolecule. Okay, so see you next time. See you later for course number 5. Bye bye. See you. Take care of you.